Okay, we are picking up in lesson 1.2 on the page starting with continuity. Okay, so it's the top of that second page there. And as we look at the front and back of this page, so you see homework on the board. That homework that says page 95, 22 through 46 evens, if I recall correctly, goes with the front and back of the page you're looking at. So it goes with continuity, increasing, decreasing, boundedness, and local and absolute extrema. Okay, if I'm recalling correctly. Now, my morning class, we got through the front, continuity, increasing, decreasing functions. And so I told them they could start the homework, but we'd finish with boundedness and extrema tomorrow. So the homework will be due on Wednesday is what we're looking at right now. And then we'll use Wednesday and Thursday to finish out the notes, I think. Okay? So that's kind of where we're headed this week. My plan on Friday, the e-learning day, is to be starting into lesson 1.3. Because I have a plan of what I want you guys to do for e-learning that involves lesson 1.3. So that is my plan of where I want us to land. Okay, so continuity. If I say a function is continuous, what comes to mind? Never stops, keeps going. What'd you say? Keeps going, so are there breaks in it? No, because it never stops, keeps going, right? Okay, so when I think of a continuous function, I think of something that I put my pen or pencil or whatever down on my paper, and when I start drawing it, I never have to pick my pen or pencil up. Okay? And that's exactly what we're talking about here when we talk about continuity. So a function is continuous. Okay, so that's what it means to have continuity, is it's continuous if there are no holes, no breaks, and no asymptotes. Okay, we talked about holes and asymptotes last year, and we're going to talk about them again today, which are breaks in the graph. So as long as there's no holes and no asymptotes, a graph is continuous. Now, in order for a graph to be continuous, we must check for these holes and asymptotes, and that's what we're going to practice right here. As we look at these fractions, do you remember what the key is with a fraction? And when we talk about where holes and asymptotes come from, how do we know where those happen? Yeah. We talked back in Algebra 2 about finding holes and vertical asymptotes. And it always happened, whether it was a hole or an asymptote, it always happened by setting the denominator equal to 0. And so whether you're looking for a hole or a vertical asymptote, that's always going to be my starting places. Okay, let's set that denominator equal to 0. Now, in this case, my denominator is x plus 2. If I set x plus 2 equal to 0, what happens? Okay, subtract 2 from both sides, and we get x equals negative 2, which officially means we say x equals negative 2, but really what it means is x cannot equal negative 2, can it? Because if you put negative 2 in that denominator, it's going to make that denominator 0, and that can't happen. How do we know if this is a hole or vertical asymptote? We know there's an issue at negative 2. We know the graph cannot continue there. But how do we know if it's a hole or a vertical asymptote? What about the numerator? No. Not necessarily. What do you guys remember about x squared minus 4? So let's take a moment and let's rewrite this. X squared minus 4, okay, put on the algebra brains, factors into 2 parentheses. X squared breaks up into x and x. This is what I call the difference of squares. The square root of x squared is x. The square root of 4 is 2. And my signs end up being plus and minus. It's coming back to some of you. Okay, so here we have x plus 2 times x minus 2 on top. My denominator was x plus 2. And I saw a lot of light bulbs go on there. What do you notice? Okay, because that denominator that presented the issue can cancel out, that means that there is specifically a whole at x equals negative 2. Because that factor of x plus 2 that gave us the location of the whole, because it could cancel with something on top, that means it is a whole. Okay, so one thing we're going to do is we're going to set the denominator equal to 0, and we're going to investigate, I call this algebraically, because we just used algebra, didn't we? We factored, we checked for canceling, that was the algebra. We're also, the other thing we can also do is we're going to investigate it graphically. And so those are the two techniques that we're going to use. Set it equal to 0 and use your algebra. And then we're also going to investigate it graphically. So, I would encourage you to, I'm not doing anything fancy on the graphs today. We will learn a new skill tomorrow. Make sure you have your calculators with you tomorrow because we'll talk about extrema, and that's a new skill to use. But, doesn't hurt to practice graphing with me, right? I'm going to do alpha f1 so I can do my fraction. I'm going to do x squared minus 4 over, what is it? X plus 2. I'm going to do zoom 6 because I don't know what I last graphed. If done correctly, your graph looks like my graph. What's the graph look like? Looks like a line, right? Now, supposedly, what do we think is happening? Yeah, we think there's a hole at negative 2. Now, if you hit trace, and I arrow left, now here's the thing. If I arrow left, mine just skipped over negative 2 this morning. Yeah. It skips over negative 2, so you can't really see what's happening exactly at negative 2. But, okay, I'm in trace. I can find the value of x equals negative 2. First of all, since I'm in trace, I could just, if I start typing negative 2 right now, it pops up x equals. And notice when I hit enter, it says x equals negative 2, y equals nothing. That means that there is a hole. What? Okay. And
were you in trace?
Yes. Yeah.
Okay, the other way you can get that, that if I'm in trace, I can type negative 2. The other thing, you remember your second calc menu? Number 1, value. That's another place because you're trying to find a value. It automatically populates up the x equals, and I can type in the negative 2. Okay, but again, having that nothing there. Oh, I bet you use minus 2 instead of negative 2.
I use negative 2.
Well, I don't know. Your calculator is totally different. I can't speak about your calculator, but I'm guessing you use minus instead of negative. Yeah. It's, I always, in my other classes, I'll always teach a minus and a negative. They're pretty much interchangeable, aren't they? Except these calculators don't believe that. So, okay. So there's our backup that there's a hole. There's definitely not an asymptote happening. If you, look there, x equals negative 2, y equals blank, there's our backup that it's a hole. Okay, so a little bit of vocabulary right there. F of x has what is called a removable discontinuity at x equals negative 2. So that is the fancy word for saying f of x has a hole. So you need to be familiar with this vocabulary because on a test, it's not going to say, is there a hole or vertical asymptote? It's going to say, is there a removable or non-removable discontinuity. Okay? Come up with a way to remember. My way is goofy because I just think, okay, it's removable. That means it's like I can remove a plug, put a plug back in the hole or something. And that's my goofy way of, remembering it. I don't have a nice math way or anything, but so a removable discontinuity is a hole. Okay. Now, let's check out the others, or this next one. In order to find if it was a hole, we set the denominator equal to 0. We saw what happened there, and we investigated graphically. Same thing is going to be true for an asymptote. Start by setting the denominator equal to 0. If I said denominator equal to 0, x minus 3 equals 0, what do we know? Okay, add 3 over, we get x equals 3. So right there, I know x can't equal 3. I know there's either a hole or a vertical asymptote. How do I know it's not a hole this time? Yeah. If it was a hole, this factor of x minus 3 on bottom would have an x minus 3 on top that could cancel out with it. There's not another factor of x minus 3 on top, is there? And so that means that this is a vertical asymptote called a non-removable discontinuity. I think of it, it's an asymptote, it's very broken, it can't be fixed. But this is a vertical asymptote. Okay. If I pull it up on the calculator so we can investigate it graphically, I'm going to use my alpha F1, x plus 6 over x minus 3. Whoops. Remember, if you don't use the fraction bar, you have to put parentheses around the numerator and parentheses around the denominator, yes? I think everyone can do a fraction in here now. If you can't, see me and I'll see if I can get your calculator to do fractions because I'm on a good run this year. Okay. Is this graph continuous? Can I draw that all at once without picking up my pen? No, definitely not. This graph is two different pieces. Okay, so this is definitely not continuous. Definitely more than a little hole, isn't it? Yeah. And if you look here, we said there was a non-removable discontinuity x equals 3. Does that make sense? If you look about x equals 3, is there room? There could be an asymptote in there? And there is. Okay. Your asymptote won't show on your calculator, but I can definitely tell that that is an asymptote. Got it? And you can even zoom out more if you really wanted to. If you're not convinced, you don't care for that graph, you can zoom out more to even see what's going on. Okay. So, and that right there was just me doing a zoom out. I just went into zoom out and hit enter and it zoomed out. So, okay, let's look at the examples here. The examples want to know, determine where the function has a discontinuity and state if it's removable or non-removable. So it's not asking, is there a discontinuity? It's saying where. And then what type is it? Which, there's denominators, right? So there's definitely going to be a discontinuity. So how do I find where the discontinuity is? Okay, we're going to set the denominator equal to 0. So x plus 3 equals 0. What do you do then? Subtract 3 over. And we know x cannot equal negative 3. So right now, I know that there is some type of discontinuity at x equals negative 3. That's the where. Now the question is it removable or non-removable? We'll go look at the graph in a moment. But before we look at the graph, remember we can look into the algebra. If it's a whole, there's another x plus 3 that cancels with it. If there's not another x plus 3 that cancels with it, it's an asymptote. Thoughts? It's not 3 parentheses. No?
Oh, that's not right.
Or x plus 3 squared, x plus 3.
Can we do? Oh my God. Can we do x plus 3 and then x squared plus 9?
Not exactly. Okay, now, the factoring's not quite there yet. However, it does factor. That's what I'm going to tell you guys. Okay, this is a special case. We did learn this in Algebra 2 last year, I promise. I'm not saying you liked it or remember it a lot, but we did go over it. So, this is what I would call the sum of cubes, because x cubed is a perfect cube, and 27 is a perfect cube. What it does is it factors into a binomial, so 2 terms, and a trinomial, 3 terms. So let me take you through the process and remind you. As I said, we did this last year, but, you know, it's been a while, right? So I'm just going to factor it right up above here. Start with x cubed. What is the cube root of x cubed? X, yes? Because x times x times x is x cubed, right? So the cube root of x cubed is x. What is the cube root of 27? 3, because 3 times 3 times 3 is 27. That middle sign stays the same. So your binomial is x plus 3, which is just the cube roots of each piece. Keep the sign in the middle. Got it? Now the trinomial. Okay, so this is where I'm going to use my x and my 3 to do the rest of this. The first term in the trinomial is the first term from over here, but squared. So we're going to take the x and we're going to square it. When you take the x and you square it, you get x squared. The middle term means you take this x and the 3 and you multiply them. X times 3 is 3x, and we're going to use the opposite sign this time. And so the opposite of plus is going to be minus 3x. And then the last one is what we did in the first one. We have to square the last term. Earlier we squared the first term, now we're squaring the last term. What is 3 squared? 9. And this last one is always a plus a number. And so, because when you square something, it's positive, so it's plus 9. Okay. We'll keep reviewing that. That is something that I introduced in Algebra 2, though. Sounds a teeniest bit familiar. I know I introduced it. I know I did, but yes.
Sorry, I was listening, but can you go over how you got the negative 3x one more time?
The negative 3x comes from multiplying. So once I get this first binomial, I use those terms. And the middle term comes from multiplying these two and using the opposite of the middle sign. So since it was plus here, I used minus. And 3 times x is 3x. I introduced it at some point. I wonder if this falls in that chapter 5 right before Christmas. I don't know. We did it.
But
It might have fallen into something that was very rushed. I don't know. I know I introduced it, but okay. Again, though, I didn't just expect you to remember it, did I? I baby stepped you through it, and I will baby step you through it every time. I still baby step my calc kids through it too. So, okay, but work on remembering how to do that. We'll talk about it more, I'm sure. But all of this to say, what happens? Yeah, there's an x plus 3 that cancels here. And if x plus 3 cancels, that makes this a whole. What's the official terminology for whole? Removable discontinuity. AKA whole. I'll be honest, my brain always goes to, okay, that's a whole, okay, now which one is it? Is it removable or non-removable? So. Okay. So just kind of beware for that factoring. Okay. Watch for those perfect cubes. Beware. They do factor. We just have to remember how. Okay. Shall we talk B? You'll like B better. It doesn't have a catch like that in there. Okay. So first of all, on B, where is there going to be a discontinuity? At positive 2, because if I set my denominator, x minus 2 equal to 0, add 2, x is 2. So we know x cannot equal 2. Now, removable or non-removable? Why?
When you factor it out.
Okay. So did you try factoring? We're not just assuming that this is non-removable because the last one is removable, right? You factored it, right? So if you look at x squared plus 3x plus 2, as I said, this goes back to the more basics of factoring. This factor you've been doing since Algebra 1. X squared is x and x, multiplying to be 2, adding to be 3, plus 2, plus 1, and notice, does anything cancel?
No.
No, nothing cancels, so we are expecting this to be a non-removable discontinuity at x equals 2. Or in other words, it's an asymptote. I just realized I skipped over graphing the last one, didn't I?
It's okay. We don't need to do that. Actually, we don't need to do that.
Well, and here's the deal. I mean, I'm just confirming it in all honesty. Okay. If we graph the one we just did, x squared plus 3x plus 2 over x minus 2. I'm going to zoom 6 because I had really zoomed out. I mean, it's kind of good to look at the graph here because, okay, this is what my calculator shows. Okay. For Carter, it's a roller coaster. If you just look at this right here, it looks like it's just all one graph, doesn't it? But what is there supposed to be? There's supposed to be an asymptote. Now, don't ever just assume, me as the math teacher, when I see this, I know that, oh, if this is going down like that, there's probably a piece up here that goes up. If I go to zoom, I think if I zoom out, so that's number 3. If I just zoom out, so if I hit enter and then hit enter again, I think it'll show you the other piece so you can see both pieces there. Yeah. That's the other piece just up there off the screen, but that's where you have to watch out, right? Your calculator might be zoomed in too much to see the entire graph. Okay, does that make sense? We said there was a non-removable discontinuity at x equals 2. That makes sense now, doesn't it? Okay. Questions? Okay. Let's move forward and talk about increasing and decreasing functions. What's it mean for a function to be increasing? What goes through your brains? Increasing. Goes up, right? Decreasing then is going to go down. Okay, so official terminology If a function is considered increasing, then as the x values increase, so does the y value. And what that's saying is, it's always going to start off as the x value increases, because what that's saying is as you move along the graph from left to right. Okay, so as the x values increase, as you go from left to right, the y values are increasing. That means our graph is going to go up, kind of like a positive slope. So what about decreasing then? If a function is considered decreasing, notice it still says as the x values increase, but now it says as the y's decrease. Because it's still, as you move across the graph to the right, what are the y values doing? They're going down. I think along the lines of a negative slope. And then the third, which I'll be honest, we don't usually use, but a function is considered constant if as the x values increase, the y values stay constant. And you'll notice an example there, horizontal line. That would be a constant function because the y values are staying constant. Okay, our job here is going to be for the function, tell the intervals on which the graph is either increasing and decreasing. Okay, now when we do this, when we tell the intervals on whether it's increasing or decreasing, we are going to use our x values to do that. Okay, so when I say that it's increasing from here to here, I'm going to give that in terms of x values, but the y values are what are going to be increasing or decreasing. Okay, so these intervals in terms of x values. So what do you think we need to do on example A here? Yeah, if we want to know where it's increasing or decreasing, we're going to have to start with a graph. You can't do this problem without knowing what the graph looks like. Well, I shouldn't say can't, but we're not going to. So, parentheses. Whoops, that's not a parentheses. Parentheses. X plus 2 parentheses quantity squared. I would encourage you to use what's provided, the x plus 2 quantity squared, as opposed to trying to like say, oh, I'm just going to multiply that out and put it in. Because, for instance, if you put x squared plus 4, that's not the same. Because you'd have to FOIL this out. Okay? I'm going to do a zoom 6 because I know I was really zoomed out earlier. Okay, what do we have here? I would call that a right side up parabola personally. Okay. Got a parabola here, yes? Okay. And what do you notice about that parabola? Where is it? If you look right here, it moved over, well, not that you can tell with my finger pointing. It moved 2 left. Could I have known that by looking at the equation that this moved 2 left? You guys all sat through a year of Algebra 2 with me last year. We did this a lot. Earlier, I'll let you off the hook for the factoring. Okay, we did that a little. Who knows when? I don't remember. But x plus 2 quantity squared. If a number is added or subtracted inside the parentheses, that means the graph is going to move left or right, opposite the sign. See, you remember me saying this? It's there, right? Okay. If the number was outside at the end, it would be up and down. Yeah, it's coming back to you. H is the one in parentheses. H is your horizontal movement. K is your vertical movement. Okay. So, we have this parabola. And just for the benefit of I want to be able to draw on mine, I'm going to draw a parabola here. And the one thing I need to know is where's that vertex at the bottom? That vertex is at -2, 0, yes? And you can tell that just by looking in the calculator, right? Now, okay, I like to think in terms from left to right. Okay? As I start in the farthest left portion of my graph, what is my graph first doing? If I'm starting at the farthest left, so the farthest left here is right over here. And if I start tracing to the right, where's my graph going to go? It's going down, yes? It doesn't matter that this arrow is pointing up. That arrow is just saying, okay, that's where my graph continues. But as I move to the right on this graph, I'm decreasing, right? My y values are going down. So the first thing we have is a decreasing interval. Now, when we talk about this decreasing interval, where did my graph start decreasing? At what x value do we start decreasing? Yeah, don't we start decreasing from the beginning? Officially, this parabola keeps going out and out, right? Gets wider and wider and gets taller and taller. So, officially then, that means from the beginning, negative infinity, we are decreasing. Negative infinity always uses a parenthesis. When do we stop decreasing? We're going to stop decreasing when we hit this minimum point. We'll talk about mins and maxes tomorrow. This minimum point, and the x value there is -2. Do we actually touch the point -2? Yes. So that tells me I'm going to use a bracket. Okay. Kind of similar to what we've been doing. If it touches the point, still bracket. If it runs along an asymptote, still parenthesis. Okay. What happens after we pass through the point -2, 0? As I continue to move my right, now I'm going up, yes? And if I'm going up, those values are increasing. When does my graph start increasing? Using x values. The point it stopped decreasing is where we're going to start increasing. So it's going to start increasing there at -2. And where does it stop increasing? Never, right? It's going to keep increasing forever, so we're going to say positive infinity. Okay, so always remember, it's as we read left to right. Okay, as we read left to right, first thing this graph does is go down, and then it hits that low point, and then it turns, it goes up. So there's our increase. We have one decreasing interval, one increasing interval. Right. There's never a time where my graph has a flat line. Very rare, if ever, will we talk about a constant interval. I honestly, I'm not even sure if we ever have one, but very rare if so. Because usually our graphs are curving, and so they're going up and down. They're not going flat. Okay. Okay, B. So what do I need to do on B? Graph it. If you're not using a fraction bar, use parentheses around that denominator. I personally love my fraction bar. So x squared over x squared minus 1. Got a 3-part graph happening with me? Okay, your graph should look like my graph. I'm going to, again, I like to be able to draw and write on mine, so I'm going to draw a sketch of mine here. Because otherwise I can put this in, you know, you can put this in your notes all you want, but, whoops, that pen is running out. Okay, not perfect, but something like that. Okay. I've got my calculator here that we can use as well. And in all honesty, whoops, I'm actually going to hit trace, and I'm going to arrow all the way over to the left side of my screen just so I can demonstrate something here in a moment. Okay. So, as I start the far left edge of my graph, what is the first thing I'm doing? As I move to the right, what are my y values doing? They're very, very slowly increasing. And that's because there was an asymptote under them, right? So yes, they're going to be very slowly increasing at first. It doesn't help that I'm going slow, but okay, eventually what happens here? 1.3, 1.4, 1.5, 1.7, 2, 3, 9. Those y values increased, didn't they? Okay. So my first interval is an increasing interval because this whole piece is increasing here, right? Okay. When did I start increasing? Off the left side of the graph. So we start increasing at negative infinity. Now, what is the end of this interval here? I want the x value. So if I hop back on my calculator here, we watched the y values last time, yes? My y values were going up. Watch the x values this time. Negative 2.7, negative 2.5, negative 2.4, negative 2.2, negative 1.9, 0.8, 0.6. Negative 1.06, and then look what happens after this. We hop down to the bottom portion of my graph, which I'm not ready to talk about yet. So what's happening right here? There is a asymptote at negative 1. And so what ends our interval there? Negative 1. Because we are increasing all the way up until that asymptote, right? Negative 1 with a parenthesis or bracket. Or we're going to touch negative 1. We can't touch negative 1 because it's an asymptote. So we're going to use a parenthesis. Well, so one thing, because as I look at, first of all, right here, I'm about as high as I can go on my graph, and it says negative 1.06. And when I go right one more, and now jumps me over here at negative 0.9. So I jumped over negative 1. Or, look at that denominator, folks. What do you know about x squared minus 1? X squared minus 1 factors into x plus 1 and x minus 1, right? And when you set the denominator equal to 0, you get an asymptote, right? Okay, hang with me. I know, I just looked at the time. Hang with me. Okay, so now, we're going to jump down here on the other side of negative 1. What is my graph doing at this point? As I'm going to, first things first, we're going to increase. What are we increasing to? If you look in your calculator, this point is at 0, 0. So what is the x value there? 0. Now, what was the beginning of this increasing interval? Negative 1. Negative 1 because we just hopped over the asymptote, right? Negative 1 with a parenthesis because negative 1 was an asymptote. 0 with a bracket because it was an actual point. What happens after we go through 0, 0? We're now going down. So now I have a decreasing interval. Where did we start decreasing? That top point of 0, 0, so the x value of 0. When does this interval stop decreasing? Along that asymptote of positive 1 this time. So 0 to 1, 1 has a parenthesis. Give me just 30 seconds. What happens when we jump over this asymptote here? We are decreasing again, aren't we? So we are decreasing, and that decreasing interval, it's 1 to infinity. 1 because we're on the right side of the asymptote, and then infinity as we go off to the right. Okay, you can look at homework, continuity, increasing, decreasing on 22 through 46 evens. I will finish up the back side of the notes tomorrow, and that makes the homework due Wednesday. Thank you for those few extra seconds.
No, that's what we're at.